All right, so today we're going to finish up our section on chapter 3 for our book. Today's going to be all about graphing transformations, which is actually not necessarily exclusively explicit or exclusive to quadratics. You can use it for all different types of functions, except some of them for linear. Um, but anyway, we're going to go ahead and look at how these work. Whoa, that is not showing up correctly. Oh, there it is. That's interesting. So transformations are changes in a graph based on changes to what is known as a parent function. A parent function is the simplest form of any type of equation. So for instance, the linear parent function is f of x equals x. Quadratic parent function is f of x equals x squared. Radical parent function f of x equals square root of x. So we'll probably see a lot of the second and third ones, quadratics and radicals, while we're looking at these examples, just because those graphs are really easy to play with and maneuver. There are a few major types of transformations that we're going to talk about. Horizontal and vertical shifts, as you can see here. Let me get this out of the way. Um, move the graph from, this is where the parent function would be, moved it left in this case. So horizontal shifts go left or right, vertical shifts go up or down, but they don't change the shape of the graph or like the width of the bits, the parabola arms, I guess. Shrinking and stretching. So you can shrink them either vertically or horizontally. So in this case, they were, I guess, stretched horizontally. It starts like this and it kind of stretches out to get further. You can also shrink it this way. For graphs like, let me see. For if I did like the graph of f or square root of x, it looks like this. It's from the x-axis, but close enough. We can stretch it vertically like this, or we can shrink it vertically like this. In this case, you could also shrink this horizontally, so it'd be more like this maybe. Could be another version of it. But yeah. And then the last one we're going to look at is reflections. So this is actually square root of x. And you can, in this case, they reflected it across the x-axis. You can also reflect across the y-axis. So then it would be going like that or somewhere close to it. But okay. So vertical transformations, these are the first ones we're going to look at. In this case, we've got a parent function here and we've moved it up to here. So vertical transformations are perhaps the easiest type of transformation. To move the graph function up or down, simply add to go up or subtract to go down the number you want from the original function. So in this case, we want to move the graph f of x squared up 3 spaces. All we do is add 3. So then we have f of x equals x squared plus 3, and that gives us this graph here. The other way to think about it is what you're doing here is effectively, if you want to move up, then you're adding 3 to whatever your y is. Remember, f of x is y equals whatever your function was. This would go up 3. F of x, I guess this would actually move it down 3. No, so this moves it up 3. You're just adding it to whatever the function is. So, you want to make sure that the function changes the same way, and then minus 3. So, whatever the function is, you either add or subtract. Horizontal transformations are a bit trickier, but they're still fairly simple. So if you want to transform a graph to move to the left or the right, simply add to move to the left. So adding will move it to the left, or subtract, which will move it to the right, from all occurrences of x. So for instance, if we want to move 2 spaces to the left, we replace all occurrences of x with x plus 2. So like if we had x squared plus 2x plus 3, we would go x plus 2 squared plus 2 times x plus 2, I'm running out of room, plus 3. So you're just replacing x with adding a number if you want to move it left and subtracting a number if you want to move it right. And the reason you can think of this is, let's say that I'm at, let's say I'm doing x squared, right? That's just a parabola that hits right here. This 0.00, if I change this to an x plus 2, I now need -2 to be my 0, right? X has to be -2 because I'm adding 2 extra to it. So that'll move it this way, like that. And then if I subtract 2, then I need x to be 2 in order to get to 0. So I'd move over to here. So that's the reason that this actually transforms things. So in this case, if we wanted to move f of x squared 2 spaces to the left, we would add our new equation as x plus 2 squared. Okay. A couple of other ones. So shrinking and stretching vertically. In order to vertically stretch or shrink a graph, we simply need to multiply to stretch or divide to shrink the graph by the amount that we want it stretched. So in this case, we want it stretched out by a factor of 2. So you'll notice that where the original graph hits 1, this one now hits 2. Where the original graph hits 2, this one now hits 4. And then it looks like it does hit 3 right here. And this one would hit 6, but we're not there. So that one will stretch it by a factor of 2. Now, 0.5x or square root x is the same thing as square root x over 2, or right at 1/2 times square root of x. And you'll notice that this is half of 1. This is at 1 when this one's at 2. This is at 1.5 when this is at 3. So it's shrunk it by that amount. For the example, if we wanted to double the point or the height of all points on the graph f of x equals square root of x, we would instead use f of x equals 2 square root x. And if we wanted to have the height, we would rewrite it as f of x equals 1/2. So that one's pretty simple. Now, horizontal shrinking or stretching and shrinking is a little bit harder. So in order to stretch, which means to pull it away from, so get wider, which should make some conceptual sense, we need to multiply or divide the x value by the factor that we want. And so in this case, it's the same idea. You're replacing x with whatever value you want it to be. So like, let's say 2x if we want to double the width. And as this will say, to horizontally stretch the graph of f of x equals x squared by a factor of 2, we would divide all occurrences of x by 2. So we would have 1/2 x squared. I might have said that backwards the first time. So yeah, we need to multiply to shrink, and we need to divide to stretch. So the other way to think about this again is, let's say we want the 0.11, right, and f of x squared. So if we have x equals 1, then we've got 1 squared, which equals 1. So at 1, f of x squared equals 1. If we want to stretch that, if we do 1/2, it's 1/2 x squared, that's the same as 1/4 x squared. And in this case, if we plug in 1 for x, we get 1 times 1/4 is 1/4. So that right here, this is only at 1/4. Over here, it's doubled our width, right? So at 2, x squared is equal to 4. 4 times 1/4 is 1. So our point would now be 2, 1. So it's basically just doubling the width of this when you divide it by half. And then vice versa. If you wanted to increase it by half, you would move it in. So now we're hitting at the point 1/2 comma 1 instead, which makes sense because if we do 2 times 1/2, we get 1, and 1 squared is 1 once again. So yeah, to horizontally shrink the graph of f of x equals x squared by a factor of 2, we would multiply all occurrences of x by 2. So the last one we're going to talk about is reflections. There are 2 different kinds. You can go across the x-axis like this, or you can go across the y-axis like this. So we are currently looking at across the x-axis. So that's the vertical one. So that would be this. Although I think this is actually a picture of a y-axis one. That's interesting. That's really interesting. I'm not sure why I used this graph. This is not the right graph for this. But anyway, to reflect a graph across the x-axis, you want to take the negative of the entire function. So if we think about it this way, f of x, let's say in the original function, f of x equals 2. So the point is, let's say, somewhere over here, right? If we make this negative, now we've got f of x. So the negative version would be -2, and that is down here. So all we're doing is taking the negative of the entire function. So we can write it out like this. So we've got f of x equals 2x squared plus 3x plus 4, which we would then change to negative f of x equals 2x squared plus 3x plus 4. But what we'll end up doing, since we can't write a function as negative f of x, we just multiply the entire equation by -1. So now we get -2x squared minus 3x minus 4. This is important to note this distinction because what we're going to do next is when we reflect across the y, we're going to make x negative. And you'll notice that on things like this right here, we have negative 2x squared, right? This is going to be a negative number no matter what x is. I guess unless x is imaginary and uses I, but we're not talking about that right now. So like if x is 10, that's going to be 100 times 2, which is 200, but it's negative, right? So no matter what, that's going to be negative. And then this is always going to be negative. Well, this one can be positive if x is negative. And then this will always be negative. So that makes a big difference in like how the graph is actually going to end up looking. Whereas what we're about to do, we'll do a different thing to it. So reflecting across the y-axis involves making all instances of x negative. So specifically making all instances of x negative. This means that wherever you see x, you would replace x with negative x. So like the one we just saw, this is a slightly different one. We've got 3x cubed minus 4x squared plus 2x. We'd replace all the x's with negatives. Negative x cubed is a negative number. Negative x squared is a positive number, but this is a minus. And then we've got negative x, which is presumably negative. So you'd have negative 3x cubed minus 4x squared minus 2x. But if we go back to like x squared, or I think it was 2x squared was the original. So when we wanted to flip this across the x-axis, we made the whole thing negative, right? When we want to flip this across the y-axis, we specifically make x negative. And when we do that, what we'd get in this case is 2 times negative x squared. Negative x squared is just positive x squared, right? They're the same thing. No matter what value of x you put in here, it's still going to be the same number, right? If x is 2, then this would be negative 2. Negative 2 times negative 2 is positive 4. If you did negative 2, then you just have 2 squared. So no matter what you put in here, you're going to get a positive out of this. And that's why it's important to make sure you know the difference between the two. So yeah, I think that's it. So this is a game. I'm going to link it on the Google Classroom. It's all about practicing these different things. But I would definitely go through and write these down. So for reflecting across the y-axis, you can just label it and then say you want to replace all instances of x with negative x. For vertical vertical reflections across the x-axis, you would say you just want to make the whole thing, multiply the entire equation by negative 1 is what you want to write down for that one. What I would write down for this one, for stretching and shrinking in the horizontal area. So if you want to stretch it by a factor of 2, you divide all occurrences of x by 2. And if you want to shrink it in the horizontal direction by a factor of 2, you multiply by 2, just the x specifically. So in this one, you can also think of it as replace x with, in this case, it'd be 2x. And then the vertical one, in this case, we'd multiply the entire equation by whatever we want to shrink it by. In the case of horizontal transformations, we're again just replacing the x with whatever we're adding. And if we want to do vertical ones, we are adding it to the entire equation. So if you think about it there's another way to think about it as like the vertical ones, you're going to be making a change to the entire equation. For horizontal transformations, your change is only going to be to the x value. So you're going to be replacing x with something. So that's kind of the simplest way to put it, I think. We can talk about this more in class if it's confusing right now, and we'll also get some practice on it. So hopefully that's not too bad, but there are 6 different versions of them, and it can be a little bit confusing to try to learn them all at once. So we will get plenty of practice. Playing the game will probably be worth your time, and it's not horribly unfun. I know most math games aren't exactly exhilarating, but I think it'll be worth your time. So give it a shot at least. It's just in Desmos, and it won't take you very long, I don't think. So yeah, but that's it for this chapter. Next chapter we will move on to after our quiz, which will be on Wednesday of next week. So that's November 4th.